Okay, this is the part 2 of Unit 4, Lesson 4.4, Probability. So we're going to be talking about compound events, complementary events, single events, complementary events in terms of what are the opposites or what are just not of. And then we also talk in terms of probability, what is probability. So first of all, we have a diagram here. And the diagram is basically showing us the two ends of our probability spectrum. So for probability, it is between 0 and 1, always. It's going to be decimal or fraction between 0 and 1. So now, for example, 0 means it's 100% absolutely impossible. It'll never happen, okay? That will give you a possibility of 0. Always, if it's going to always happen, okay, regardless, you have to come to school, okay, that's going to be a 1, okay, 100% of the time it has to happen. The sun will shine, whether or not we actually see it, because it might be behind some rain clouds, the sun is shining somewhere in the world, okay, so the sun will rise every day. So certain events versus events that'll never happen. Then we talk about an even chance. Even chance means you got a 50-50 shot. Okay? But we don't talk in percentages always. Most people talk, for example, they think that probability means a percent, but probability doesn't mean a percent. Probability actually is a decimal between 0 and 1, and then you convert to percent if they ask you for it. And this is where we get lots of distractors for this unit. If they only ask for probability, they do not want the percent, so don't change it to percent. And those percentage distractor answers are always there to confuse you, just in case. Okay, so you have to know to look beyond that. So we've got some definitions we need to go through. So here's our probability basics. When we talk about probability, it is known as showing the chance that something is going to happen. So it's the chances of an event occurring. Now, a couple different definitions here. The first one, a trial is an event in an experiment, okay? The trial happens in an experiment. And it says it's an operation where the result can't be predicted. So, for example, maybe you're in chemistry class and you're pipetting a certain amount of fluid, and you want to see if the chemical mixture is going to change color, okay? Those kinds of things. So again, you're going to be doing an experiment, but you don't know because maybe you're using different amounts of each solution. And are they going to mix? How much do you need of each, or is it going to dilute it? Those types of things. Okay, so again, it's probability, and lots of them you can't predict. Okay, but there are many we can, which is why we do probability. Okay, and we do statistics. So tossing a coin, rolling a die, playing with cards. An event is basically something that happens in your experiment and has a sample space for it. So, we're going to do examples of sample spaces. I'm going to show you what those are in a moment. So, an outcome is actually one of the events or one of the outputs that happens from the input. So, if you want to flip a coin, the event is flipping, and what it lands on is the actual event. Okay? That's going to be your outcome, if it landed on heads or if it landed on tails. The sample space is all of your outcomes written together. Okay, that's what your sample space is. Now, we're used to seeing sample spaces with our Venn diagrams. They were given to us as lists with those curly brackets. So yes, we're seeing those, but we can also have different types of sample spaces. So a lot of sample spaces we use are charts. So we're going to see T-charts a lot, and we're also going to see dice charts. Okay? And again, we know that an impossible event is probability of 0, and a certain event that it will happen 100% of the time is going to be probability of 1. So probability notation is always written with the capital P for probability, and then you're using just normal parentheses brackets. So you're using these types of brackets. And the event goes inside the brackets, the event that we're looking for. Okay? Now, if they're saying probability of your event is 1/2, that's a 50-50 shot. That's like flipping a coin. You've only got two choices. It's like turning a light switch on. You're either going to turn it on or you're going to turn it off. Two choices, that's it. Okay? Let's take a look at how we actually calculate probability as an equation. So the equation is right here. It is the number of favorable outcomes. So the amount that, for example, if you're looking for how many times heads showed up out of 50 times we flipped our coin, heads would be considered our favorable outcome. We would count how many times it showed up. Our possible outcomes, the total possible goes on the bottom. So it's always like this. You can simplify it by doing this. Probability of what you want over the probability of the total. It's always want over total. So what do we want? What are we looking for in the experiment? And then what's the total possible for that experiment? A fair game is when somebody has an equally likely chance to win. So most board games are built that way. They're supposed to be built as a fair game, dice games, those kinds of things. And again, how do you know if you're equally likely to win? Well, you've got a 50-50 shot at winning. Or if there's 6 of you playing a game, you have a 1/6 shot at winning. Okay? Any question? No? Okay. All right. Here's an event. It says a fair die is rolled. What is the probability of rolling a 6? So we would write it like this. Probability, my event I'm looking for is a 6. So probability of a 6. How many 6s are on a die? 1. And we're dealing with a standard die, so it would be 1 out of 6. Okay? So, when we're talking probability, again, it's going to be a decimal or a fraction. When we're talking about a die, 99% of the time, we're going to be talking about a standard dice. Okay, a standard die. If they talk about a standard die, that means it's a normal 6-sided die. But they're going to be using other ones. They're going to be using tetrahedron dies, which are 4-sided triangle dice. And they do use those, okay? So you have to pay attention on which type of dice they're using. So if they say a standard die, it's 6 sides with 6 numbers, 1 to 6. And then if they tell you a different type of die, they have to tell you what it is. And we have a couple examples coming up. Then we're talking about cards. And again, like the example we showed a little while back with our Venn diagrams, if they want to talk about a deck of cards, they have to show you the deck of cards. Because a lot of people in different cultures were never raised growing up playing cards with their grandparents. Some of them have never learned how to play. I've had some international exchange students that had no idea how to play a game of cards that was actually ace to king. They played with other types of cards, you know, all kinds of different cards and tiles, but not the ones we would normally play with. So again, those are the differences why they have to tell you what you're actually playing with. So, we've got a deck of cards. If it's a standard deck, there's always 52 cards. Always 52 cards, 4 suits of 13 each. Half are black, half are red. So we want hearts or club. So we have to write down how that would be written. Well, that would be written like this. We want a probability of a heart or club. That's how it will be written because we want the symbol for or. Okay, so this is our or symbol. Now, for probability, when we use the or, that's adding in probability. So we would add. So, how many hearts are in the deck? 13 in 52. How many clubs are in the deck? 13 in 52. Or means take all of both. So I would add them up, and I get 26 in 52, which is exactly half. So half of the deck has hearts or clubs. Okay? That's basically what it's showing us. So let's take a look at what a complementary event would be. So, many think it would be the opposite of our event. So it would be written this way, with the prime tick. But we also know that it's not always the opposite, especially when we do our shading. It's everything that that is not. So if we're just simply talking about odd or even numbers, yes, it's an opposite. But remember, if we're dealing with a Venn diagram or things that have different numbers in different spots, we have to be very cognizant that it could be using other parts. So for example, if I've got numbers like this and I have an outlier of 10, and I say I want A prime, and if this is A and that's B, well, A prime is everything outside and part of the B circle. So you have to be cognizant that it's not just the opposite. It won't just be what's in B. It's going to include the outliers if there's outliers. So, one thing we have to remember because of that situation is, in probability, the probability of the event and its complement will always equal to 1 whole, so 1.0. So, the probability of event A plus the probability of its complement equals 1.0. So up here I have the probability of hearts and clubs. What other two suits are in the deck? Spades and diamonds. So we know half the deck has hearts and clubs, half the deck has spades and diamonds. And exactly, that would be a 1-to-1 split. The complement plus the event equal the whole amount. So, for example, we're going to write that one down. Whoa. Probability of heart or club is 1/2, and the complement, heart or club, is 1/2. And if we add them, 1/2 plus 1/2, we're going to get 2/2, which is 1 whole. So we do end up with the complement and the event equaling 1 whole. Okay? Let's go through a few more examples and figure this stuff out. So, compound events. Compound event is where you've got repeated trials happening. So, maybe you are flipping a coin, but you do it 10 times. That's a repeated event. That's a complementary event. Or sorry, a compound event. So, again, this one here is talking about it's either repeated or multiple events. Okay, so you're repeating things or you've got multiple things happening. So, you can flip a coin, spin a spinner, and roll a die. 3 different things happening. Or you can have a deck of cards and pull 3 different types of cards out of your deck. Okay, multiple different events. So, sometimes you can use tables, tree charts, or ice chart diagrams. We're going to go into some sample space diagrams right away here. So the first one says we have a die and a coin. So if I wanted to draw out a die and a coin, I would have my dice, I would have my D for dice, and I would have 1, 2, 3, 4, 5, 6. I would have 6 coming out of my dice with the numbers 1 to 6. And then off of each of those, I would have 2 spokes coming off, and they would have head, tails, head, tails, head, tails. So I'm just going to show one here because I don't have enough room. I would have a head and a tail coming off each. Okay? So basically what you're getting is you're going to get a 1 and a head, a 1 and a tail, a 2 and a head, a 2 and a tail. And that's what your sample space would be. So since I've got 6 numbers on a die, and I have 6 choices, and I have 2 choices for my head and tails, what is my total outcomes going to be, what do you think? If I were to continue that list over on the right, how many would I end up with? Well, I would end up with 6 for heads and 6 for tails. So I would have a total outcome chart of 12 happening. So how do I get 12? You could also get the total 6 here and times by the total 2 there. So 6 times 2 means I should have 12 things written over there as my sample space. So let's write it out as probability notation. So it says we want to know about how to get a 3 and a tails. How often does 3 and tails come along? So we want probability of a 3 and a tail. All right. What's the probability of the 3 showing up? How many times will it show up? 1. Once in 6. So that's 1 out of 6. And how many times does the tail show up? 1 out of 2 choices. So 1 and 2. And in math, for probability, the and means multiply. So we're going to multiply. When we multiply top to top, bottom to bottom. So this is going to give us a 1 in 12 shots. Okay, so that's the probability of it having a 3 and a tail. Okay, it's going to be a 1 in 12 shots. Now, if we were to write this whole chart out, we could have also just looked down our chart and circled the 3 and the T for tails. And that would have only showed up once. That's what this is telling us, is that the 3 and the T only showed up once. Yep. So 1 times 1 is 1. 2 times 6 is 12. Yeah, it's these two together and these two together. Yeah. Top to top, bottom to bottom. Okay? Alright, let's take a look at the next one. A coin is flipped and a card is drawn. So what is the probability of a head and an odd number? So we want a head and odd. So O for odd. So it says ace is considered a digit 1, which is an odd number. So we've got the numbers 1, considering the ace, 3, 5, 7, and 9. So how many odd numbers do we have? 5 odd numbers. But we've also got that in every suit, right? We have odd numbers that are going to be in hearts, diamonds, clubs, and spades. They're all going to have odd numbers as well. So we need to take this and times it by 4. Okay, so how many odd numbers am I going to have? 5 times 4 is 20. So I'm going to have 20 choices of odd numbers. Okay, so my odd numbers, my choices is out of 20. And I just want one odd number. So I'm picking one card. I'm just writing it right underneath this so you can see which part matches. Alright, and I'm flipping a coin. How many choices on a coin? 1 out of 2. Alright, and it's saying and. So and means I need to multiply these. So I'm going to multiply top to top, bottom to bottom. And I'm going to get 1 in 40. So there's a 1 in 40 shot of getting an odd number and sorry, ahead. Now the odd number, we got to go back to this. I made a mini error. How many decks are in the card? Or cards are in the deck? 52. So we have to put 20 over 52. Because we had 20 cards to choose from, we only needed one of them. So 20 cards were odd out of 52 cards. I have that fraction wrong. So 20 cards out of 52 of them. So we're going to get 20 in 104, which reduces to become 5 and 26. Okay, so 5 and 26 is what it ends up being. Alright, let's take a look at the next one. We have 2 coins and a spinner. Alright, so we want to get the probability of a head and a tails and a blue. That's what we want to get. The and intersection means multiply. So 2 coins. What is the choice on a coin? How many total? 2 choices. I want a head is 1 out of 2. Tail, 1 out of 2. Now it says I want to get a blue spot on the spinner. But we have to take a look at how many spots are on the spinner. We've got 1, 2, 3, and 2 yellows. So there's 5 spots on the spinner. So how many are blue? 1 in, 5 are blue. Alright, and now we're going to multiply. So we multiply all the tops together, and we multiply all the bottoms together. So we're going to get 1 in 20. So we're going to have a 1 in 20 shot of getting a head, a tail, and a blue. Okay? Next one. We want to get both heads and a yellow. So now we're going probability of a head and a yellow. Alright, heads we know are 1 and 2. Times 1 and 2. Times. Alright, how many are yellow? 2 in how many? 5. Good. So multiply all your tops. Multiply all your bottoms. 2 and 20 should give us 1 and 10. Okay? 2 and 20 gives us 1 in 10. All right, let's take a look at an actual sample space. So it says, consider the following events. Tyler's a student and he did the following experiment. He tossed 2 coins and he said, I'm going to look for the probability of getting 2 heads, so a head and then a head. And he says this, my sample space should give me a head and a tail, and then 2 tails. And he's looking for 2 heads. He's saying 2 heads are going to show up once out of how many times? 3. Well, let's see if he's right. So we need to draw a tree chart. So we're going to draw our tree chart for the first time. So we're going to start with a coin. And coin 1. This is coin 1. If I have a coin, I have 2 choices. A head and a tail. Now I'm going to flip coin 2. Well, coin 2 has 2 choices. A head and a tail. A head and a tail. So, coin 2 versus coin 1. We need to now see how many total outcomes do I have. Well, if we were to write our sample space, I would have head, head, then tail. On the bottom, tail first, then a head, then another tail. So how many total outcomes did I get?
So coin 1 has 2 options, but coin 2 has 4.
Well, coin 2, you have to think of it this way. If we got a head on the first coin, and I flip coin 2, I still have 2 choices. But these are what it could land on. Okay, so this is the total number of choices. You have to consider each situation separate. So, coin 1, we have 2 choices, but we don't know what it landed on. Because it could have landed heads or it could have landed tails. So let's say it landed on the tails. Well, if it landed tails, I'm going to flip another coin. And then it's got 2 choices again. It's either going to land on a head or a tail. So, dude up here says he only got 3 options, but we get 4. What didn't he consider? Yeah, if you take a look, those show up twice, head and tail, just in a different order. But it does matter. It's still part of the question. So he's considered this as one outcome. But is it actually one outcome? It's not. Because this one said you flip the head first. The one down here says you flip the tail first. So the order does matter on these ones. So that's where we would say we've got 1 out of 2 for a head times 1 out of 2 for a head. So we should get 1 out of 4 spots down here that say HH, head. And if we notice, there's 1 out of 4 that say head. Okay? And that's why we get 1 over 4. He got 1 out of 3. He didn't consider this being 2 options because you could get the head first versus the tail first. Okay? So you have to remember those. Now we're going to look at a different one. We're going to look at a dice chart. So let's look at our dice charts. This is a 6 by 6 dice. Okay? So this is you taking a pair of dice and you're chucking them down and you're saying, all right, what showed up? So what we would do is you would add the sum of them. So they're showing you a 1 and a 1 showed up. If we were doing the sum of them, this would be 2, 3, 4, 5, 6, 7. Now I want to show you the pattern it makes. What's 2 and 1? 3, 4, 5, 6, 7, 8. What's 3 and 1? 4. So what are you noticing about each? They're starting, but they have each number less. This guy starts with a 2. The next one starts with a 3. Then he starts with a 4. What's the next one starting with? 5, 6, and then a 7. Okay? That's how our charts work when we're talking about what they add to. So if I'm going to add the sum, okay, so the sum of the digits. So then this would be 5, 6, 7, 8, 9. The biggest thing I want you to notice is all of the like pairs will be diagonal. So if I'm looking for ones that add to 4, they're always diagonal. Okay, so you're looking for numbers that are diagonal, typically always. So we'll just finish writing this out so we can see the other numbers when they come up here. Okay, so the following ones, it says, we want the probability that the dice is going to land on the same number. If it lands on the same number, you're going to have a double. So, 2, 4, 6, 8, 10, 12. They're always counting by twos if they have the same number showing up. So how many did I get that showed up? How many numbers have the same? A 1 and a 1, a 2 and a 2, a 3 and a 3. Showed up 6 times out of 36 total. How do I know it's 36? I can count every box, or you just take the total of each die. 6 total, and multiply them. Okay? So now we're going to math wrap that down. That would be 1 and 6. Okay, you always reduce. The next one, we want everything not the same number. So this is the complement. So if I want the complement to that, all I've got to do, literally, the complement and the original add to 1.0. So all you've got to do, if I have a 6 on the bottom, that means I should have a 6 at the top for one whole, right? Top number should add to 6 for complement. So if the complement is going to be 30 out of 36, which is 5 and 6. Because if I add these two numbers, they have to add to 6 over 6. If I add the big numbers, they have to add to 36 over 36. Okay? Because it's the complement and the event. Okay? A sum of 8. Well, now we're going to look at the ones that add to 8. So I would diagonally add them up. So I've got 1, 2, 3, 4, 5 of them that add to 8. So you'd say I have 5 in 36 that add to 8. Okay? The next one, you have to know your greater than and less than signs. So this one's saying greater than 9. That means it can't equal 9. So the part I'm looking for on my diagram then, I want greater than 9, I want the 10s, 11, and 12. So that means I have 6 numbers. Okay, you're looking for the numbers greater than 9. Well, I've got 3 10s, 2 11s, and a 12. So that's 6 numbers. So I have 6 out of 36, which is 1 and 6. Number 5 says less than 8. Less than 8. Well, I have 8 right here. I need to count how many are on the left-hand side of 8. So I've got 1, 2, 3, 4, 5, 6, 7. Actually, I'm just going to go across this way. 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22. So we have 22 numbers that are less than 8 out of 36. And again, you're going to math wrap that down to 11 and 18. So 22s or 21? 21, yeah. You know there's something wrong there. So it's 21 numbers, not 22. So that's going to be 7 and 12. Okay, event 1 and 2. Well, event 1 and 2 we already talked about. They are complementary events. Okay, they're complementary. Let's try this sum less than 6. And what does the word or in probability mean? Add. So same thing here, or. I'm just going to erase my coloring up here so we can do other coloring if I need it. So, a sum of 4 is the ones that add to 4. So, these guys add to 4. There's 6 numbers. So, 6 and 36 add to 4. Now I got to find less than 10. How many are less than 10? Well, if I do 10 and bigger, there's less numbers to subtract, or I could just add them up. And we should get 30 and 36. So 30 and 36 are less than the digit 10. Yep. Only 3 of them add to 4? No, 3 and 1, 2 and 2, 1 and 3. Oh, sum of 4. Thank you. It's only 3. I thought I was doing less than 4. Thank you. It's 3. Okay, so now we're going to get 33 out of 36, and that's going to reduce to 11 and 12. So both divide by 3, just math frack them. All right, yes, don't get caught like I did, read the problem correctly. So the next one says sum less than 6. So now I'm going to color less than 6. So that means I have to add 5. Adds 5, adds 5, adds 5, so it's all this. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers that are less than 6. So 10 and 36. Or means add. Some bigger than 10. So they have to add to 11 or 12. I have 2 that add to 11 and 1 that adds to 12. So 3 and 36 to give us 13 and 36, and that won't reduce. So that's as low as you can go on that one. Okay. Example here. Okay. So we have a transportation and we have a children one. We're going to do the one with the transportation. So this one right here, we're looking at when certain trains arrive to the train station. So this one says train A arrives from 7:11 to 7:16. So that's why we've got 7:11 to 7:16. It says train B arrives at 7:13 to 7:17. So we want to know when do they arrive at the same time. So at the same time would be 13 and 13, 14 and 14, 15 and 15, 16 and 16. So if I want to find out the total number of outcomes, I need to take this number and multiply it to that number, because I need to know how many squares I have. So I've got 1, 2, 3, 4, 5, 6 choices on top. I've got 5 choices on the left. So how many boxes would I have? 30 boxes. And how many landed on the same time? 4. So A would be 4 in 30, which reduces to 2 in 15. Okay? 4 in 30 reduces to 2 in 15. All right. B says, determine the probability B arrives before A. Well, if I want B arriving before A, the blue is when they arrive at the same time. Okay? So if we look at right here, is train B at the train station yet? Right there. No, because he doesn't arrive till 7:13. It's not 7:13 yet, it's 7:11. Thanks, you read according to the top. So this guy here, he's not at the train station yet. He's not at the train station yet. Oh, yeah, there he is. Okay? Then he's there. So they arrive at the same time. This guy's not there yet. So this would be them arriving at the same time. Here is where train who arrives first. This is where A arrives before B. And this is where B arrives before A. And that's what we have to know. So if we say the probability that B arrives before A, I just count up how many squares I've got. So I would have 6 squares. So B would be 6 squares out of 30, which is 1 in 5. Okay? C, I want the complement to this B. Well, if I want the complement just means what would add to 5 over 5. So letter C, the complement, something equals 1 over 5. I need this guy to add on top to 5. So what would the complement be? It would be 4, because these have to add to the bottom. So the complement is going to be the 4. Okay? All right, we have 2 diagrams left. We will take those after lunch. Okay, now we're looking at a different type of a tree chart. This one is having children. So if I said to you, a couple's going to have 3 kids, is it fair to say I would take my diagram and I'd say, okay, you're going to have, there's my C, I need kid 1, kid 2, kid 3. So am I going to go kid 1, kid 2, kid 3? Does that make sense? Are we all unisex? Because that means we're having kid 1 that's unisex, kid 2 that's unisex, and kid 3 that's unisex. That's what that says. So the way we draw them, you wouldn't believe how many people pick this one all the time. I'm not kidding, it freaks me out every year. So, you're going to have a couple. They're going to have a kid. Chicago's pick a kid up. What are we going to do? 2 choices. We only have 2 choices, folks. Boy and girl. Boy and girl, according to our DNA. Boy. Girl. So because of this, there's kid 1. So kid 1, we have a chance. It could be a boy or it could be a girl. We don't know. So now we go kid 2. Well, what if we had a boy first? Well, we could have a boy again, or we could have a girl. What if we had a girl first? Well, we could have a boy next, or we could have another girl. Then we have kid 3 come around. Kid 3, same thing. I could have another boy, or they could have a girl. Or we could have another boy here, or a girl. Boy, girl, boy, girl. So if I want to know how many total possible choices there are for having 3 children, I would count up how many red ones I have now. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So my total would be 8. Okay, so we're going to write that down. Total equals 8. There's another way I could find that total out. What is the probability, what is the number of choices to get a child? How many spokes did I draw? 2. So for kid 1, I had 2 choices. For kid 2, 2 choices. For kid 3, 2 choices. What's 2 times 2 times 2? 8. Okay? So if you take the individual number of choices per event, you'll get the total amount of choices. Okay? And that total amount of choices is important. So now we're going to look here. All boys, no boys, 2 boys and a girl, at least 1 boy, at least 2 girls. So when we're dealing with these, we have to deal with writing our sample space out. So our sample space is going to look a lot like the outcome chart. So I'm just going to extend this longer just so you can see what the outcome chart would look like. So the first string we had boy, boy, boy. Then we had boy, boy, girl. Then we had boy, girl, boy, boy, girl, girl. Then the next ones all started with girls. Okay? So we could have girl, boy, boy. Whoopsie. Jump around. Girl, boy, boy. We could have girl, boy, girl. We could have girl, girl, boy, or girl, girl, girl. So, these are all of the possible 8 outcomes. And this is the order they could have them in. This isn't random. This is the order. So you'd have a boy first, then another, then another. Okay? So when we look at these outcomes, we're going to answer the questions now. So A says, how many of these have all boys? 1. So A, 1 in 8. There's 1 in 8 of these choices. 1 of them has all boys. The next one says, no boys. Well, what's the complement to all boys? No boys. Well, the no boys would be all girl, girl, girl. Okay? So that would be 1 in 8. Because all no boys means all girls. Okay, does that make sense? If you're saying you have no boys, that means you got all girls. Yeah. So now, letter C says 2 boys and a girl. Doesn't matter the order. So now I'm looking for 2 boys and a girl. There's 2 boys and a girl. There's 2 boys and a girl. There's 2 boys and a girl. How many times did it come up? 3. So we'd have 3 in 8. D, at least. The word at least, I want you to write minimum. So minimum, 1 boy. Well, minimum 1 boy, that's everybody except for the all girls. So that would be 7 in 8.
Are we able to start with factorial at the exclamation point?
That's the next unit. Yeah, that's our last unit, unit 5. Okay, letter E. It says at least 2 girls. So that means minimum 2 girls. So that means we're looking for 2 girls or all girls. So here's 2 girls in green, there's 2 girls, there's 2 girls, or all girls. How many have minimum 2 girls? 4. So, 4 in 8, which is 1/2. Okay? Any questions about how to look through those? Again, if they're tree diagrams, make sure you write the outcome chart to help you solve questions. Because if you're just looking at the diagram to solve the questions, you need like 5 highlighters to kind of follow where they go. Okay? All right, last example. These are the ones that everybody likes because they're super fun and easy. Yeah, I said fun. Okay. So what we're going to do is, we always talk about the event and the complement, and that's what we write down here. So if I'm talking about rain, what's the complement of rain? No rain, right? Rain or no rain. So we're going to have rain and rain prime, which is no rain. Okay, if you wanted to literally write no rain, you can, but he's rain prime. Okay, everything but rain. So we have 3 places: Vancouver, Toronto, and Edmonton. Now, it's only going to tell us one number. Okay, you need to be quiet, please. They're going to tell us one number. The reason they tell us one number is because we're supposed to realize that that number plus the complement equals 1.0. So if I know the probability of something is 0.4, I just subtract from 1, and the other one is 0.6. So we're saying the probability of rain on Christmas Day in Vancouver is 0.75. So then what would be the no rain? 0.25. Good. But see, they're not going to give you this information. They're only going to give you the one. You have to realize to do the other. The next one says Toronto is 0.68. So now we're going to take 1.0 and subtract 0.68. And that's how we find our complement. And what would that be for no rain? 0.32. Edmonton, it says 0.12. That's right, because it's always snowing on Christmas. So, 0.12, what's the opposite of 0.12? 0.88. Good. So now we've got our chart filled out. That's the part, and they're not going to show you to build a chart. You have to know the information. So if they're only giving you one piece of information for each event, that means you have to do a chart so you can do the complement. So here they're saying, what is the probability of rain on Christmas Day in all 3 cities? So that means Vancouver and Toronto and Edmonton. So that's the and. Okay? So that means I'm going to take all 3 numbers of and multiply. So I'm going to have 0.75 times 0.68 times 0.12. And that's what I'm multiplying together. And it wants 4 decimal places. Good. 0.0612. So that's the answer for that one. So for it to rain on Christmas Day in every part, in all 3 cities, basically a 6% chance if we change it to percentages. Okay? All right. Now we want rain on Christmas Day in none of our cities. That means it wants no rain, no rain, no rain. So now we take and we do 0.25 times 0.32 times 0.88 to get our answer. Good. 0.0704. Okay? The next one says it wants probability of rain on Christmas Day in at least 1. At least 1 means minimum 1. Now let's listen to the concept. If it's got to rain in at least one of the cities, that means it can't rain in none of them. Does that make sense? If it's supposed to rain here and Red Deer and in Spruce View, it's supposed to rain there, and they say it's got to rain in at least one of those 3 places, the opposite would be not raining in those places, right? That's the complement. So if it says at least 1, they're saying it's 1 and minus the probability of none. This is your complement. They're showing to use the complement because it's easier. So we know the rain in none of our cities. This is rain in none. So now we're going to take 1 minus that. And that's going to be how much it'll rain minimum in at least one of them. 0.0704. So 1, subtract that. It should be a big number, exactly. So 9296.9296. Okay? So probability of it not raining anywhere, and then this is the probability of it having to rain in at least one of those places. Okay? So you're always going to subtract the complement of it not happening. Okay, last one. It wants both Vancouver and Toronto, not Edmonton. So literally you're going up to your chart and you're looking for snow in Vancouver, snow in Toronto, not Edmonton. So you're needing to know which ones to multiply. So you want snow, snow, no snow. Okay? So that's the numbers in the order you're multiplying. So we're going to take 0.75 times 0.68 times 0.88. Okay? And that's going to give us 0.4488. So 45% chance it's not going to rain in Edmonton, but it'll rain in the other two places. Likely it will, because we'll get the snow. Okay? This concludes lesson 4.4 of probability.